use that material. All right. We left off talking about molecules. Okay. Simple definition of molecules is that I have two or more atoms, at least, combined together. And when molecules combine together, they have absolutely different properties than the two elements that came before them. What was the example I used last time? What was it? Table salt. Okay? Can you eat table salt? Will you die? Slowly, because of hypertension. But what were the two things that it was made up of? Sodium, metal, chlorine gas. If you take in sodium or chlorine, what will happen? You will die. So you go from dying immediately to some compound that actually is necessary for your body in small amounts. Okay, it can be detrimental in large amounts, but totally different thing. And so we have molecules. They're also called compounds, and so molecules and compounds can be interchangeable. All right, in terms of what you see. Now, when you talk about compounds, there are two principles by which we have discovered something about them. And it happens so often that it has moved from the realm of theory into what we call a law. And a law is something that has been repeated and repeated and repeated, and it always comes out. And so we are confident that it's not a theory anymore, but actually something that is a fundamental idea. And so the law of constant composition says this: any particular molecular compound has a defined and the same number of atoms in it for every molecule that exists. And so for sugar, let's say, it is always 6 carbons, 6 oxygens, and 12 hydrogens. Okay? That is what sugar is. In particular, this is a glucose molecule we're talking about. And so every time we see glucose, it always has that composition. And so for every compound or molecule, there is a defined composition. Now, we also found this, something called the law of multiple proportions. There are times at which compounds can be made from the same two elements, but they can combine in different ratios. The most common example that we talk about is carbon dioxide. Where do you get carbon dioxide? When you breathe out, or when you burn gasoline. So carbon dioxide, 1 carbon, 2 oxygens, and carbon monoxide. What's the difference between carbon dioxide and carbon monoxide? One has 1 carbon, one has 2. Okay. What else about the two? Which one is deadly? Carbon monoxide displaces oxygen in your hemoglobin, which oxygen is really important. And so carbon monoxide is very, very poisonous. Carbon dioxide can, in high concentration, get you, but in low concentration, carbon monoxide can kill you. Another, yes?
Wait, isn't it 1 oxygen, 2 oxygen? Or something? I think that's 1 carbon, 2 carbon.
Oh, it is. Carbon dioxide is 1 carbon, 2 oxygens, and carbon monoxide is 1 carbon, 1 oxygen. Another common proportion that you might have is how hydrogen combines to oxygen. H2O is water. H2O2 is hydrogen peroxide. They're very close in their proportions, but totally different. One you can drink. Well, actually, both of you can drink, but one is good for you and one is not. And so we can see that there are ways in which two elements can combine in different proportions. Now, a definitional item. Substances, okay, can be classified. There are 2 ways in which you find substance. One is pure and one is not pure. We call that a mixture. Okay? Pure substances, there are 2 kinds. You can get a whole bunch of pure molecules. Okay? And so everything in your sample would be the same molecule like water. There's nothing else in the container. Or you can have a pure element. The single atom If you have it all pure in a container, it is a pure element. I will tell you this, purity is very hard to reach. And so even when I go to a chemical company and I buy a pure chemical, they sell it to me at 99.9% pure. We consider that pure. Is that absolutely pure? No, it's very hard to get something very pure. You can actually go and buy things that are 99.9999% pure, okay, if you really need a lot of purity, but then you even purify that even further. And so theoretically, you can have pure things. It can be either a molecule or it can be an element, but those are the things that can be pure. Other than that, in the real world, not very much is pure. So we also talk about mixtures, and we'll talk about that just a moment. Okay? The mixtures are really basically everything else. A mixture can be physically separated, okay, into the components that are there. Now, there's lots of techniques to separate. We're not going to talk about how to separate in detail, but let's say this. Is the water coming out of the faucet tap pure? No. You can taste some things sometimes, right? That means there's some sort of stuff in there. If you go to a well, you may even get water that doesn't even look clear. Okay? So a way to purify that is to distill it. Heat it up, boil the water off. All of the impurities, or a majority of the impurities, do not boil. And so as the steam goes over, I get purified water on the other end. And so that's one way to separate, using a physical property, boiling point, two components. Now, there are two types of mixtures, one called homogeneous and one called heterogeneous. Okay? A homogeneous is called a solution. Now, what is the difference between a homogeneous and a heterogeneous? This is the simple definition. If you can see the particles that make up the mixture, actually see them with your eyeballs, it is heterogeneous. I can see the two things mixed up together. Okay? If you can't, if the two items are dispersed so evenly that you cannot see the difference, then it's a homogeneous. Sometimes chemists call it a solution. Okay? And so if by chance you placed a glass of water on the table, okay, and you want to play a trick on somebody, you might put in some salt and stir it up. Okay? That glass with the salt in it looks perfectly fine. The salt is distributed so evenly that you cannot actually see those particles. But when would you detect that there's salt in it? When you actually drink it. Okay, so that is a homogeneous mixture or a solution of salt water. Okay? This ring I have, okay, it's 24 karat gold. It's my wedding ring. Okay? Is that pure gold? It's the highest content of gold that you can get in jewelry, but it is not pure. Why do you know it's not pure? If I squeeze on this, does it bend? No. Gold is very soft. If I squeezed a piece of gold, it would actually bend. So this is actually a mixture of metals. Okay? This is a solid solution of metals. We have a solution that is liquid. We also have a solution that is solid. A solution of metals is actually called an alloy. Just a terminology to throw in there. And the air that you are breathing, is it pure? No. Do you know from any other class what is in the air that you're breathing? There are two main gases, nitrogen and oxygen. Can you see those pieces of nitrogen and oxygen floating? That is a mixture. It's a solution of gases. And so you can have solutions of solid liquids and gases. We usually use the term solution as liquid, but solution is more broad. Okay? Heterogeneous. Has anybody ever been to LA? If you look at the air, is it nice and pure? No, it isn't. That is a heterogeneous solution of gases. It's with a smog in it. Okay? And so you can have mixtures and you can have that are heterogeneous and homogeneous. And it is dependent upon how well or how distributed the materials are mixed together. And so if we start with matter, okay, we can look at it, is it uniform throughout? Or is it yes or no? And we can determine if it's heterogeneous, homogeneous mixture, and all the way through pure substances. This is a decision scheme about how you might approach something looking at it. There may be an example on the exam that asks you and gives you a list of 4 things on a multiple choice question. Which one is pure, a pure element, or which one is a pure compound, or which one is a mixture? Something like this. Air. Oh, we've already identified. What is air? Is it a heterogeneous mixture? Is it a homogeneous mixture? What is it? Homogeneous mixture. And I need to sink my pencil. Hopefully that works. Not enough. Okay, what about gasoline? Has anybody actually seen gasoline? Okay, usually you pump it in your car and you don't actually see it, right? But sometimes you can. And so, if you look at gasoline, it actually looks clear. But gasoline has all sorts of things in it, and so this is a homogeneous mixture. And this one was hetero. Okay, water. Okay, that is a, if it just says water, it's assuming that's the only thing there. And so that would be a compound, and it would be pure. Soil. Heterogeneous. You got rocks, you got dirt, you got all kinds of stuff. You may even have a worm. That's heterogeneous. Gold.
What kind?
In this case, what is it saying? Is there anything there other than that, other than gold? So what is it?
Pure element.
Pure element. Okay. Hydrogen. Pure element. Table salt. Pure compound. All right. Milk.
Mixture.
Okay. Depends upon where you get your milk from. Has anybody ever milked a cow? Okay. When you milk a cow, what rises to the top? The cream. And so in real milk coming from the cow, you actually get layers, and that is a heterogeneous mixture. But if you pour out a gallon-sized milk out of Mayfield's bottle into a glass, what does it look? It looks homogeneous. Have you ever read the side of a milk carton? It says that it is homogenized, meaning that it had been layers, and they process it so that it is a homogeneous mixture after processing. And that's what that term homogenized means. You may not have known what that meant. And so it depends upon milk. This is a really bad question. Milk from a cow, okay, I can do that. Or milk from the store would be 2 different answers. Okay? Pewter. It's a mixture, but what kind of mixture? It would be, is it heterogeneous or homogeneous? It is homogeneous. It's all silver, pewter is, and it's mixed, and you can't pick out the lead and the silver pieces. They're all mixed together. So this would be a homogeneous mix. And oxygen, element, and a pure. Okay. All right. Some more definitions, and I'm sorry that the first chapter is a whole bunch of definitions. Okay? But when we do measurements and quantification in chemistry, okay, 2 big pieces that are important. One that is hugely important and one that is less important. The less important is the number, although most people focus on that. The largest thing that is very important is the unit. What does that number mean? Neither one are important if they are missing, if they're not put together. Okay? So for something to mean or be important in chemistry, you have to have a number and a unit. So there are some base units that we define everything from. And these are the base units. The amount or mass is measured in kilogram. The length is measured in meter. Time is measured in second. That little a up there means that you could also write SEC as second. That's definitional. The temperature that we use in scientific measurements, that is definitional, is Kelvin. The amount is mole. Electricity is ampere. You'll use that in GChem-2. And light intensity, the candela, is something that you would use in physics. Okay? And so these are the definitional units. But if you buy a Coke in a bottle, what size bottle do you normally buy in the store? Liters. Liter is a measure of what? Volume. Do you see volume on here? Fundamentally, volume is something we use all the time, but is not one of the base units. Volume can be derived from one of these units. Any other unit that we use, like, let's say, speed, your velocity. When you drive down the road, how fast do you drive? Don't give me a number, but you drive in what? Miles per hour, okay? A distance over a time. That can all go back to one of these, or a combination of these 7. So a speed in science is what? Not miles per hour, it's what? Meters per second. I can change meters per second into miles per hour. I can do those conversions. But everything that we measure in scientific terms can be derived from these basic 7. You need to know these 7 and their designated units. Okay? And so, let's say a freshman guy walks on campus and he weighs 100. What would you think?
100 what?
100 what? Okay, if he's 5 foot and weighs 100, okay, 100 pounds, that might be something that you might expect. But if he weighed 100 kilograms, that would be 220 pounds. That might change the mental image of that picture. Okay? And so, we must give both of those. Unfortunately, you're geared to putting numbers in a calculator, and that's the important part, and I got to get the right number. Unless you have the unit, it doesn't matter. And, quite frankly, what I'm going to tell you is the way we calculate things is based upon not the numbers. It is based upon what does the unit tell me to do with this problem. That is where the strategy comes from. The units will tell you how to get from one place to the other. That's where the logic comes. And so, when we do this, we always have to have the measurement in terms of a number and a unit. Okay? And so, a car is not just 12, it's 12 feet long. A person is not just 6, they're 6 feet tall. And so, if by chance you are multiplying things together, you can multiply the number together, but you also have to multiply the unit together. And so, they manipulate mathematically just like numbers. And so, to get an area is a length times a length. So, a length could be feet, a length could be feet, but the area is foot squared. And so you have to have that part. Or speed, a car traveling 350 miles in 7 hours is not a college student driving home, because no one would be driving at 50 miles per hour. But in this case, the numerical value of 350 is divided by 7. That's where we get the 50. But the mile is also divided by the hour, and now the unit becomes miles per hour. That is the unit for this value. And so you have to manipulate both the number and the units. Okay? If the car travels for 3 hours at this speed, you would have traveled 150 miles. And in this case, if I do the mathematics here, what we see is the hour and the hour cancel out to be 1, so it mathematically goes away, and I'm left with miles as the only unit. I multiply the two numbers to get the 150, I multiply the 2 units, and I'm left only with miles. And so units must be mathematically manipulated just as the numbers. All right. Now, when we take measurements in chemistry, we have to have a number and we have to have a unit, but we also have to have a measure of certainty about how good are you doing, okay? And in English, we use these two terms interchangeably, but in chemistry, they are different. The terms precision and accuracy. And so if someone actually asked, are you precise or accurate about something, they're mainly outside this building asking for the same thing. Did you do a good job? Did you get it right? Okay? But that are two separate different measurements. Okay? In this, precision is measured as this. Every time you do an experiment or every time you make a measurement, does the measurement come out close to each other? If I measure my height, does it always come out to be 5'10"? And you do it again, it's 5'10", good. Do it again, it's 5'10", good. I can be precise. Okay? Or if you place something on the balance, it always comes out to the same value. Or you use a ruler, it always comes out the same value. You can be absolutely precise and dead wrong. Okay? If by chance someone in the lab reset the balance and put it off, the 0 mark off by 2 grams. Then you can take your sample and measure it every time you get 22 grams, and you measure again 22 grams, and you measure again 22 grams. You would feel pretty good that it weighs 22 grams. But if it was set, the 0, not at 0, but at -2, you would have precisely measured 22 grams every time, but the weight was actually 24. You would not have been accurate. Accuracy is agreeing, the value that you measure agrees with the value that is true or real. Okay? And so being accurate is actually getting the right number. Being precise is getting all of them always measured the same way every time. So at the top, good precision, good accuracy. At the bottom, or in the middle, poor accuracy but really good precision. They're wrong exactly the same way every time. And then the last, hopefully it's not your exam, you have poor precision and poor accuracy. Okay? So that's on a dartboard. How does that look in chemistry? Okay? What we're going to be looking at is data. All right. Let's do this. What about D? Is it accurate or is it precise?
Is the goal to be on the line?
The goal is to be on the line. That is the true value. So is D accurate or precise? None. Okay. How about A? Both. It is accurate and it's precise. Okay. What about B? Okay. It has no accuracy, but it is precise. Now, how in the world do you know precision? You see that they're grouped close together. All right. Mathematically, we take an average of that, okay, to see where they are, and we would look at the standard deviation, how far away they are. Okay. And we know it's not accurate because why? The average of those numbers, does it agree with 25 in B? No, it agrees with a different number. What about C? Is it precise? No, it is not precise. Is it accurate? What if I say it is accurate? The average of all the data set, actually, if you actually take the numbers and you do an average, it actually comes out to the right value. All right, here's the deal. In most cases in science, especially in biology, where there's a lot of variation, very rarely are you very precise. But you can get accuracy if you sample large enough samples to weed out the varying ups and downs to get the true average. And so even though your data set may not be precise, it can actually become accurate as long as you take enough data points. And so in science, taking more data points is always best. It makes more confident your measurement. Now, in laboratory, we may grade you on precision and accuracy. When you go into the lab and you do your work, what is the only one that you can evaluate yourself? Which part of that? If you take 4 measurements in lab, would you know if you're accurate or would you know if you're precise? You would know if you're precise. That's the only thing that you can know about because we know what the real value is. And it's an unknown and we're going to test you. You won't know if you're accurate. Here's the rule of thumb. If you go in and you are precise, most of the time you're accurate. Okay? You have a much higher chance. If you go into the lab and your numbers are all over the place, okay? You're not feeling real confident about what you're doing. Okay? You're getting numbers all over the place. By chance, you could be accurate. But how likely is that? If you take just a few number of samples, the likelihood is not great. But if you take a huge number of samples, the likelihood increases. And so if you're not being precise, you have to take a lot of data to try to get towards accuracy. And so for you, in the laboratory, you're aiming for as precise as you can. And with a small number of samples, the more precise, the more chance you're accurate. Okay. Now, it could be and so what we're looking for to know if you're accurate, we're looking at the average of the data set compared to the real value. Okay, the average of the data set. The precision, we're looking at the spread. How far away are they from each other? Okay. So, when you make measurements, they can be accurate and precise, but I also said you had to identify a number and a unit. Okay. There are 2 kinds of numbers that we deal with in laboratory or on problems, and this is probably where you're going to deal with it most often. Okay. There is the exact number. Okay. And an exact number is this. If I look at the classroom, I can count how many male and how many female. I will not get numbers like 12 and a half female. Okay? I will have 12 females in the class. If you can actually physically count something, it is an exact number. That means its significance is infinite because you know it exactly. Okay? Also, a conversion factor or defined unit has an infinite number of significance, meaning that it's that, there's no question about it. There's no uncertainty. Okay? A true number, if you can actually count it. Very rarely will you be able to count things in lab. Most of what we do is a measurement that becomes an inexact number. Means that there is some error at all times. So if you use a ruler, okay, you can look at the lines and know where the lines is, but if something's between a line in terms of its length, who tells me how big it is or how long it is? You have to make a judgment. Okay? And that judgment has error. Oh, wait a minute, but I can measure the mass accurately every time because I put it on a balance and the digital scale tells me exact number. It tells me 12.001. That's perfect. As long as I write it down, right? That should be exact, right? Well, it gives you an exact number to a certain level, but the guess in this, the estimate, is in the precision of the instrument itself. And every instrument has a plus or minus built into it, and it's told to you. So even if you use an instrument that gives you a numerical value and it prints it up on a piece of paper, that number is somewhere close to that, plus or minus a certain value. And so every measurement that you actually do, unless you're counting, is uncertain or inexact. So if you take a look at this, and you look at that nail, okay, they estimate it to be on this, they estimate that to be, the length to be 6.35. Okay. Of those numbers, the 6.35, which ones can you rely on? Absolutely. Okay, the ones we can absolutely. Is it 6? Yes. It's definitely 6. It's gone past that line, right? Is it at least 6.3? Absolutely. Where did we make our guess? The in-between. This last number right here is the estimated one. When we make a measurement, we always report as many significant figures as we absolutely know, and we estimate one more. And that estimation, depending upon what you're using, can be defined, a plus or minus, or in this case, we know it's there, but we're not exactly sure how much is that significance there. And so every number that is written, and that means every number in a problem, means that there are some numbers that we absolutely know, and there's one number that we guess. And we're making an estimated guess. And so, if a balance has a standard error of plus or minus 0.001, and I put the sample on the balance, what is the weight of the item that you're measuring? It is not 2.552. It is what? Between what and what? It can be as heavy as 2.55 what? It can be as light as 2.551 and as heavy as 2.553. It is somewhere in between, and we're going to guess that it is 2.552. But it can be anywhere in that range. Okay? And so even though it's written for you, there is some sort of error that's associated with every measurement that you take. Sometimes we formally tell you by plus or minus exactly what it is. Sometimes we don't tell you what the plus or minus is, but what you should know and recognize is that last number, whatever number is given, is an estimate. Okay? So significance is all the absolutely known values plus one digit that we guess at. Okay? If I formally give it to you like this number with a plus minus and everything, you know exactly what's going on. But most of the time I'm just going to give you a number. So I'm going to have you define for me how many numbers of that are significant. And so we have rules. And so the rules for reporting significant figures are this. 1, all non-zero numbers are always significant. So 1, 2, 3 has 3 sig figs. How much for the next number? How many sig figs? 4. Okay. 3 of them are absolutely known. 1's guessed at. Zeros between numbers are significant. So 101 has 3. What about this next number? How many sig figs? Okay. This one and that one are good because they're whole numbers, and it says any zeros between them. So 1, 2, 3, 4, 5, 6. 6 sig figs. All right, zeros are where we get the big issue here. Zeros before the first non-zero digit are not significant. They're just a placeholder so that you can see where the decimal place is. So this one is not, because it's before, so that has 1 sig fig. How about the next number? How many sig figs? Just 1. Even though there's lots and lots of zeros there, it is before a non-zero number, so it doesn't count. All it does is place the decimal place in the right area. All right, again, another zero question. Zeros at the end of a number, but after a decimal point, are significant. Okay, so here is 3. Why is this 3? That one's significant because it's a whole number. Zeros after the decimal place, okay, at the end of the number are, but zeros that are before a non-zero number are not. So that's why that's 3. So how much in the second one? 3. All right, now let's throw a loop in everything. The number 40,600 with no decimal point is a booger. Okay? This could be 3 because that one and that one is rule 1. And this one's between that, so that's rule 2. So it can be 3, but it also could be 4, and it also could be 5, but we don't know. And so writing a number this way is not good to determine how significant the number is. So what we're going to do is use scientific notation. Okay? This is why we use scientific notation, is to make sure that you know the significance of the number. And so, because the decimal is here, what I'm going to do in scientific notation is move the decimal so that I have a single number, point, and then the rest of the number. So I have to move that over 1, 2, 3, 4 times. And when I do that, I get, stop. When I do that, I get times 10 to the 4th. Okay? And so I get 4 point something, 0.6, at least that times 10 to the 4th. If I write it like that, it's 3 sig figs. If I wanted to write it 4, I'll put in another 0, which fits the rules. And if I wanted 5 significant figures, I would write this the additional 0, because now this number fits the rules to say it's all 5. Okay. Now, once you know the numbers and number of significant figures, then significance can only be, if you use them in calculations, you can only be as significant as your least significant measurement. And so, if you multiply, this is the rule that we use. When you multiply, you're going to get something in the calculator. You never, ever put what's in the calculator in an answer box, because there is way too many decimal points that you're never that accurate. For multiplying and dividing, what you do is you have to look at the least significant number that you multiplied or divided, and that's what you can report. So here, how many sig figs? 2. How many here? How many here? What can my answer be? 2. And so 2, and then I write potentially 3, but what do I have to look at? The next number, right? And what's the next number? 4. Do I round up or down? you round down. Anything 0 to 4 is down, and anything 5 to 9, you round up. And is this answer right? Not without a unit. You always have to have a unit. Okay. Adding and subtracting are a little bit different. Adding and subtracting, you look at the least number of decimal places. Not the significance of the whole number, just the number of decimal places. And so this is what you put in the calculator. Never put that into an answer box. Okay, 1, 2, 3, 4, 5 decimal places here. 2 decimal places there. So I have to use 2. So I write the whole number plus 2 decimal places, which would make it what? 1 and what? 0 or 1? 0. And I have to write milliliter. Okay? Rules for significance. Stop. All right. How many sig figs in 246 in this one? 5. That's all rule 1. How about here? 1, 2, 3. Zeros after decimal place are 4, 5. Okay, what about this one? 4. Numbers are, and zeros between numbers are 4. How about here? Numbers are, zeros after a decimal point after a number are, but zeros before numbers are not. What about this one? 4. All the numbers and a 0 before is not. That's actually a weird number. You would never write that. And what's the last one?
1.
Depends upon how you write it. You know there's at least 1. But the way that it's written, it could be 1, 2, 3, 4, 5, or 6. What if I put a decimal place right there? How many would I have? 6. You would actually have all of them. So if I put a decimal, all of them are significant. Okay. All right. Have you seen these before? Okay. You hopefully should have seen these before. When we write scientific notation, we have to write times 10 to the something. And so we write the number times 10 to the... But let me tell you, scientists are lazy. We don't like writing things out. So instead of writing times 10 to the whatever, like if I have 1 times 10 to the minus 3 meters, that's a lot of writing. So what I'm going to do is, instead of writing, let's say 1 times 10 to the minus 3 meters, I'm going to write this. 1, this prefix, milli. And by putting that prefix, what do I not have to write? Times 10 to the minus 3. So this prefix tells us I don't have to write all this extra junk. And it is a quick shorthand. And that is exactly why we use these prefixes. Now, most of the time you learn deci, centa, milli. Sometimes you use micro in classes. Kilo, which is 1,000 of them. The ones that you probably maybe not have seen is mega, although megabyte is one that's used, and gigabyte, meaning mega is 1,000,000, giga is 1,000,000,000, and then nano, you might have heard of nanoparticles, okay? But pico and femto might be smaller than you used previously, but all I want you to know is, if that prefix is there, what is the number it represents? Times 10 to the whatever. Having those down and memorizing them one specific way will be helpful to you from this point on. Okay? And so this is just a memorization tool. I'm sorry, you have to memorize a lot of things. The last thing that we are going to do is temperature. Now, what was the definitional temperature? Kelvin. Very rarely do we ever use Kelvin. You never pick up a thermometer and it measures Kelvin. So outside today, it's going to get up to 88 degrees. Uh-oh, I've said a number. What did I not say about that degrees? What unit? What is 88 referencing? Fahrenheit. Between Fahrenheit's weird. Water freezes at 32, boils at 212, so there is 180 degrees between that. Okay? Most of the time we use something called Celsius. Water freezes at 0, melts at 100. That's a nice, easy number of 100 degrees. Kelvin also goes between 273 and 373. Actually, 0.15 to add to both of those. And that's 100. Kelvin starts 0 at the absolute coldest it can be, absolute 0, and goes up from there. Okay? Celsius is what we use most often in the laboratory, where we have the reference of 0 to freeze and 100 to boil water. And then, just because we're American, we use Fahrenheit. Okay? Just to be odd. Now, the ratio to this is 180 to 100. What can that be reduced to? What over what? 9 over 5, or 100 to 180 equals 5 over 9. Have you ever seen conversions equations that have 9/5 and 5/9? That is the reason why we have 5/9 and 9/5, is because one has 180 degrees between freezing and boiling, and one has 100. And so, depending upon what you are given, you can interconvert between those. And this is a simple mathematical substitution. And so I hope you will be able to do conversions between Fahrenheit, Celsius, and Kelvin. The only equation I don't give you is what? From what to what? Fahrenheit to Kelvin. To go from Fahrenheit to Kelvin, you have to have an intermediate step. And so watch out for that. But you should be able to do the homework number 12, 13, 14, 15, and 21. I will teach you next time how to do the other questions, and you'll be